Okay, amazing. Let's get started. So yeah, this will be a we talked about some basics of modular arithmetic and something like addition, subtraction in a modular arithmetic. Now today what we'll try to do is mainly like try to look at um, try to look at division mainly. That's what we'll start with, and then we'll see where it goes. So what do I mean by this? Okay, let's fix something like mod 7. So everything we are working with, we're only working with 7 numbers: 0, 1, 2, 3, 4, 5, and 6. And then 7 is equivalent to 0, 8 is equivalent to 1, and so on. So now the question that we ask is, okay, how do we find something like 1 by 2 here or 5 by 3? So how do we find these things? So like, do you guys have any idea as to how we
Yeah,
can?
we are thinking about inverses as fractions, right? Yeah. Don't
Yeah,
we have
yeah.
to specify that? Because if just giving out 1 by 2 and 5 by 3 is just very
True.
weird.
That is true. That is true. So what I mean when I say 1 by 2 is the multiplicative. That's an excellent point. So otherwise we could have just spent a lot of time debating on things.
Second lecture of
Multiplicative inverse of 2. What do I mean by this? It's just like some number which when multiplied by 2 gives us 1. That's what I'm going to mean when I say 1 by 2. Sorry, Imon, you were saying something. I didn't hear you properly.
is this the second lecture of modular arithmetic?
It is, yes.
Okay.
Can use LT.
Huh?
Because
What? Sorry. Riansh.
we know that 2 power 6 is congruent to 1 mod 7. Therefore, 2 times 2 power 5 is congruent
Oh,
to.
this is some. Okay, okay. We haven't even discussed all of that yet. So, like,
Oh,
at some point, you would really like to state and prove that. Okay, so basically what we're looking for is, okay, hopefully like people applied 2 gives us 1 mod 7.
Your
So how
voice
many
is
such numbers are there and how can, oh, I am. Okay, am I back now? Is it better?
yes. Yeah.
Okay, thanks. Okay, so now what we want to find is a number which when multiplied by 2 gives us 1 mod 7. So first of all, okay, the question says, does such a number even exist? Does such a number even exist? And if it does exist, then how many such numbers exist? How many? And okay, again, when I say a number, I mean like a number which is equivalent to one of these things. So these are going to be our only numbers for now. Right? Okay, so I would like want to hear from people who are seeing this for the first time. And what do you think? Like how do we go about solving this? Feel free to just unmute and spit out ideas. Or you can put it in the chat. But chat is like very hard for me to monitor. Okay, yeah, what number? You want to find the number which when multiplied by 2 gives us 1 mod 7.
infinite.
How infinite? There's okay, are you saying there's infinitely many such numbers?
Yes.
Okay, can you give me one of them?
4.
Yeah, 4, right? So 2 times 4 gives us 1 mod 7. What else gives us 1 mod 7? You said there's infinitely many such, right?
11.
11 also gives us, because 2 times 11 is 22, which is again 1 mod 7. That's right. But is 11 really a different answer from 4 as such? Yeah, I see it in the chat. Guys, please unmute and answer it so that I will be happy. And happy say is like a good thing to have in life. So yeah, I see some nice ideas in chat. So basically, if you have anything which is 4 mod 7, that works. So if you multiply 2 by anything which is 4 mod 7, you're going to get 1 mod 7. So yeah, such a number does exist, and maybe 4 is a number. Mm, is there any other number that works for this? Can we have any other number which when multiplied by 2 gives? We are a little bit shy. Don't be shy. Don't be shy. You've not even turned on your cameras. It's fine. You can just like, what are you worried about? Like, are you worried about uh like people judging you? I don't think anybody's going to judge you or anything. So I give you full guarantee of that. So don't be shy and make Saee be happy by unmuting and answering. It's always nicer when there's a discussion in class rather than just me talking on and on and on. Okay. Don't be shy. Don't be shy. Yeah. So 4 mod 7. Let's also quickly look into whether there can be any other solution, right? We can just quickly verify that as we only have 7 cases. So for example, 2 times 0 doesn't give us 1 because it gives us 0. No, only one remainder. Yeah, we can quickly verify this one. If we have 2 times 1, it doesn't give us 1, it gives us 2. What is 2 times 2? Can we just quickly complete this table? Can you people like just unmute and tell me all these things? I'm just going to make you unmute and tell me like things so that somebody will be talking. Unmute and tell me things. This is like kindergarten stuff. I just want to like hear voices. Oh. Yeah, exactly. Just like unmute. I just want to hear voices. Don't put it in the chat. This is not done. I am sad. Look, I should not be smiling if I'm sad. I should be like, I don't know, sad.
I mean,
Anyways,
since
yes, 4, 6, 1, 3, 5. So indeed, that's very cool. So we only have like one inverse of 2. Okay, interesting. What about 3? Does 3 have any inverse, and how many inverses does 3 have?
No, no, no. 3 has only one inverse, that is 5.
Okay, interesting. 3 has only one inverse. Okay, 3 times 5 is 1. Okay, interesting. So we will again have 3 times 0 is 0. 3 times 1 is 3. I'm just going to write these out because why not? I like doing work. Uh, 2, 3 times 4 is. What is 3 times 4?
5.
Yeah. 3 times 6 is 4. Ah, very interesting. How very interesting indeed. What about for does 4 have a multiplicative inverse? 4 does not have a multiplicative inverse. Damn. And why is that?
Oh,
Oh, yeah. 2. Yes, of course, because 4 times 2 is 1. So 4, the multiplicative inverse of 4 is 2. Okay. Yes, Riyansh, thank you. Okay. And okay, 5. 5 is the third. Okay, as we have seen already, it's 3. And what is it for 6? So for 1, it's obviously 1. For 2, it's 4. For 3, it's 5. For 4, it's 2. For 5, it's 3. And for 6, it's
X.
oh, yes. Okay. This is very neat. Like there's already a lot of observations that you can make here. So if you're seeing this for the first time, do you see any like cool patterns anywhere or any observations about anything at all?
I have a doubt.
Yes, Gaurav. Thank you for speaking up. What is
Uh,
the doubt?
Actually, can we unmute and ask if we have not understood the concept?
Yes, I would absolutely love if you unmuted it and asked if you have not understood a concept. So please go ahead and ask.
What do you mean by multiplicative inverse? Actually,
Okay, that's a great question, right? I did not properly state that. That's very good. Thank you for asking. So what I mean by a multiplicative inverse is basically the in like a usual number line thing where we have infinitely many numbers. Two, the multiplicative inverse for 2 is 1 by 2. Multiplicative inverse for 3 is 1 by 3. Or to put it more rigorously, it's a number. So the multiplicative inverse of a number x, the number x is a number we usually denote by 1 by x or x inverse, such that the product of these two numbers, x and x inverse, should give us 1. So for example, over here, the multiplicative inverse of 2 should be a number which when multiplied with 2 gives us 1. So 2 times 4 gives us 1. So 4 is a multiplicative inverse of 2. Does that make sense, Gaurav?
yes, thank you.
Yeah, you're welcome. Okay. All right. So yeah, so now we were just listing down all the inverses somewhere. Where did it go? Yeah. No, I don't see it. Where was it?
Somewhere on the right.
It's there on the right. Ah, yes. Thank you. Okay. Okay, so in on just like on this page, there's like a lot of cool things to observe. So maybe if anybody who's seeing this for the first time, do you notice any sort of pattern, even if you think it's like trivial? Yeah, these are like the inverses that I've noted down. These are the inverses. So the 1 is the inverse of 1, 4 is an inverse of 2, 5 is an inverse of 3, and so on. So already there's like a couple of things to notice here. Even if it seems like a silly thing, any cool pattern that you see or any cool observations that you have in whatever the calculations or scribbling that we have done.
Fact sake, 2 4 sum is 1 minus 1 mod 7 and 4 2, and for odd like 3 5 it is 1 mod 7.
Interesting. So you're saying if we take the addition of the inverses here, we'll get this gives us -1 and this gives us 1. That's a very interesting observation. But it doesn't always seem to work, right? Because for 1 and 1, you're getting 2. For 6 and 6, you're getting 5. It doesn't seem to always work. Maybe it does generalize to something later, but for now it doesn't seem to work. Hmm.
That difference is always 2 or 0. 0 for same numbers and or 2.
Okay, I see where you are going. So you're trying to look for additive properties in multiplicative inverses. So you're saying, okay, this is 0, or this is 2, this is 2, this is 2. That's a very interesting observation. Let's try to verify it quickly. Let's also like look at some other mods. So this was for mod 7, right? What other mod should we look at? Give me some nice number you want to try looking at. 8. Mod 8. Okay. Can you tell me the inverses? What is the inverse of 1?
That's 1.
Yes. 2.
Not possible maybe.
Huh? Not possible? What? Why not?
5.
Like 2 divides, so inverse of 2 doesn't exist to mod 8.
Interesting. Can somebody give a that's like excellent. That's excellent intuition. And like I mean, obviously it's also correct. So good job. But maybe more something more rigorous. Something. Okay, I see. GCD of 2 and 8 is not 1. Okay, interesting. So you're saying that if it were to exist mod 8, would have GCD 1 with 8. I like this argument. So Nikhil is saying 8k plus 1 is odd, right? So what do we mean when we say we want to find inverse of 2? We want to find a number 2 times something x. It should give us 1 mod 8, which means 2 times x has to be 8k plus 1 for something. But we know that this is always going to be even, and we know this is going to be always going to be odd. Yes, great job, Aishwarya, Nikhil, and people who made this argument. So, and also I think Paras also had some similar ideas. A bunch of people had this similar idea. So nice. So to pa, that's like the sound you get when you like don't have an inverse. Okay, so two want to be having an inverse. What about for 3? Does 3 have an inverse?
That's 3.
The inverse of 3 is just 3. Interesting. 4?
No.
4 doesn't have, and
Yeah, and then 5.
5 inverse is 5 only.
5 also has itself. What about for 6?
It doesn't exist, and for 7, it's again 7.
Very, very, very interesting. So this conjecture that we had here that the difference is either 0 or 2, that still seems to hold true. So this is the differences are all 0 here again. Very interesting. Also, we had like a nice discussion. So let's also try to generalize that and prove that. So one thing that we discussed was if you want to look mod m, so if a number, let's say if a number a is such that GCD of m and a is not equal to 1, then what can we conclude?
Then it doesn't have any inverse.
Yes, then A does not have an inverse mod M. Okay. Do people see how to prove this? Right? How do we want to quickly just in 2 minutes just do the proof for the sake of doing it?
Can we have A is equal to
So,
Px and
yeah.
M equal to Qx?
Right. So first step what we know is that GCD M and A is not equal to 1. So let's call it something. Let's call GCD of M and A as D. So let's say M is equal to some D times X, D is equal to D times Y. So what do we mean when we want to find an inverse of A mod M? We want to find let's call it A inverse. which when multiplied by A gives us 1 mod M, is 1 mod M. But if something is 1 mod M, it means it's some number times n, so it's M times K plus 1, right?
I think we can suppose
Now,
that
what do we do here? Yeah.
like we can
Sorry,
suppose
Riyans,
that
go on.
A times A inverse is equal to MQ plus 1.
Yes, so that's what, let's say there is an inverse, so this will happen. So
So then
how do
the
we finish the proof from here?
so then the left side is divisible by D, so the right side must be
Yeah.
divisible by.
So D divides A, which implies D divides A times A inverse, which implies D divides MK plus 1. Right? And how do we finish from it?
That would imply that 1 divides D, therefore D equals.
Yes, that would imply that D divides 1, because we also know that D divides M, which implies D divides MK. So that means that it must divide. So D divides MK plus 1 and it divides MK. So it means that D divides 1, which implies that D is equal to 1. But that's a contradiction because we assumed it's. Can you guys hear me? Right?
We can't see the screen
Yes.
and facing some lags too.
Sorry about that. Just give me 1 minute. I'll look into it.
No problem.
Okay. It should be better now. Can you guys hear me and see me all right?
Yeah.
Okay.
Yeah, fine.
Let me share the screen again. Yeah. I'll just repeat the ending part of the argument. So now we know that D divides MK and D divides MK plus 1. But that would mean that D has to be 1. But that's a contradiction because we assume that the GCD is not equal to 1. So contradiction. Okay, very neat. This will be the general flow of the class. We try to make some observations as we go and then generalize them and prove them. Okay. Okay. So for any questions on this argument?
Again facing lags.
Sorry, Iman?
Lag.
Say that again, please. Okay, okay, no questions. All right. All right, okay. Let's try to do it for some so for even for 8 this seems to work. Okay, give me some other mod and we'll try to see if this conjecture of difference 0 or 2. Okay, first of all, do people think this is always going to be true, that the difference between the inverses is either 0 or 2 always?
Try mod 11.
Mod 11. Okay. So Lavish is challenging this. So we're saying, okay, try mod 11. So, okay, just help me out with this because I'm very bad at calculations and stuff. I'll just write this down. You guys unmute and tell me what this is.
One sec. Mod 13, I think 3 and 9 are inverse.
Okay, that already works. So thank you, Rian. So mod 13.
Mod 13 works.
3 and 9 are inverses, right? Because 9 3s are 27, which is 1.
2 and 7
And
also.
this difference, yeah, 2 and 7 also works. Yes, great. So this does not seem to be true. Also, maybe I can try to give more intuition as to what kind of observations you can look for. So since these are multiplicative inverses, it doesn't make too much sense to look for additive properties in the sense that trying to add or subtract inverses. I'm not sure if that would give us much. But maybe try to look for some multiplicative properties about this, or even anything like silly that you observe in this, or even in this tables that we have written down.
They form pairs.
They form pairs. Most of them will seem to be forming pairs because one is paired with itself, but everything else, 2 is with 4, 3 is with 5, and 6 is paired with itself. That seems to be true in mod 8 as well. So everything is paired with itself, okay. Interesting.
Inverses are bijective.
Inverses are bijective. That makes, okay. That's an interesting claim. So the claim is that what does that mean? So you guys did FEs last week, so you know what bijective means, right? So there's an interesting conjecture that inverses are bijective. Before we even do this, there's like something that seems even more silly. First of all, like for us to talk about bijection, the inverse has to be a proper function. So what do we mean by that? If there has to be so modulo m, and let's consider A such that A comma M is 1. I will not write GCD, I'll just write brackets. So this means GCD of A and M is 1. So there exists a unique inverse of A. And by inverse, I mean multiplicative, obviously. Mod M.
What does the
Do you guys
inverse
think this is true? Yeah?
What does the inverse
By
mean?
inverse, I just mean yeah, a
I
multiplicative inverse. By this exactly what we have been seeing here, like 3 and 9 are inverses mod 13. So the observation is that for every number, there can only be one number which multiplies to 1.
I think it's true.
Okay. It feels like it should be true. Oh, the E, the in ulta E. This means there exists. There exists. It's just too big to write, so you just like shorten it to there exists. Even like unique is too big to write, so you can also shorten it to like just an exclamation mark. So this reads as there exists unique multiplicative inversion. Okay. Okay. So any this does seem to be true so far, right? We haven't yet seen an example where two things have where one thing has two different multiplicative inverses. Also, even before that, why does there have to exist I'm saying there exists a unique multiplicative inverse. Before that, maybe somebody can question me and say, haha, Saee Didi, why should there even exist a multiplicative inverse in the first place? Maybe we have only gotten lucky so far that we have found the inverses. How do you know that always there will exist a multiplicative inverse? And that's maybe also something to think about. Does there always exist an inverse? And if yes, then how can we find it? And if yes, how to find? Right? So that these are some interesting questions that come to my mind. Do you have any interesting questions that or any other observations that you may have that we could, think about? Before we actually work on these things, let's think about some more interesting questions or observations that we can find from this.
Didi, I have a doubt.
Yeah, ask.
Actually, when modular arithmetic was invented,
Hmm. Oh,
like,
when was it invented? Is that what you're asking?
yeah, like at which time? Like,
I actually have no clue about this. We can Google it. When was modular arithmetic
It was or
invented?
always there, right? It's a very basic idea. It was formalized maybe later, but
Hmm. Yeah, as a formal system, it was developed by Gauss in 1800. Interesting.
uh,
This is new to me as well. Okay.
yes. But actually, what do you think? Like, why mathematicians do such strange things, finding multiplicative inverse or etc. Like,
Oh,
so
that's a great question. So, I will start maybe like divert a little bit to a story. Like 100 or 150 years ago, there's like a great mathematician called G.H. Hardy, and there's a quote of his that I find amusing. That he says, he was asked, why do you do number theory? It literally like he says, I do number theory because it literally has. Okay, don't take my word. Something not word to word, but he said something like it has no applications anywhere whatsoever. And then like 150 years later, his work is being used in like things like cryptography right now, where you like the reason we are able to securely communicate right now, or your bank accounts are safe, or your texts are safe. It's all because of cryptography, and like the base of cryptography is this. More it's like number theory and all of these things. So there's an interesting problem that comes up after this, that you can show that you cannot solve fast, or it's not actually shown, but sorry, it's a really hard problem that you cannot solve it fast. Nobody has been able to solve it fast enough. If you can solve it fast enough, then like all of our it's like a problem in modular arithmetic, all of our like security and stuff is compromised.
what are we talking about here?
Like the problem of finding logarithmic what's it called, like log mod m, like that's like or like even factorization. If you that a lot of the scripta stuff is also like based on the fact that you cannot factorize things fast. So this is all like number theory and stuff. Maybe
it's
we
simple.
can like yeah, it's definitely very interesting. So in like today's date, everything you do almost would surely, even if it doesn't have, I feel like it's a personal opinion, but surely everything will eventually maybe have some or the other applications. And why do mathematicians do things is like just part of the fun of it. Like if you go more into something like groups and stuff, then just like it's all about abstract algebra is all about making it as abstract as possible and trying to remove all the numbers from it and make it even more abstract and stuff. Anyways, that was like just this yeah. Okay. Wait, I see something in chat. Saee yapping about applications of NT in real life. So true. I can yap about things for a long time. Anyways, what were we discussing before that? I forgot. I have yes.
Saee, I guess
There's
we should
nothing but
answer
inverses,
this.
and if yes, then no, I did not hear what you said, Lavish.
I
Oh,
think you
my
should
net
turn
is
off your
bad.
video because network is lagging. Yeah.
Yeah. I'll do that. Yeah. Today I'm not in my usual place, so that's why the issues. But okay, I'll just keep it off. Hopefully it should be fine. Anyways, we move on to whatever we were doing earlier. So we go back to whatever we were doing earlier. Does there always exist an inverse? And if yes, how do we find it? These are the questions that I thought of from some conjecture. I don't know who made. I think Rayansh had this conjecture of bijection. Okay. Yeah. So, any other interesting observations? Even if they don't seem like much, even like this observation didn't seem like much, right? That they come in pairs, or even like the observation that there always seems to exist a unique inverse, or there always seems to exist an inverse. Try to think about such observations. Maybe in like these tables, if you see anything, maybe we can stare at it for a minute. You guys can tell me if you see any seemingly silly observations. So there is no such thing as silly observations, but okay. Oh, till that time, I will just put the laptop on charge. Yeah, okay. Okay, do you have any other observations or questions that we can work on? Not enough data to make a pattern. All right, fair enough. Fair enough. Maybe we can go here. Okay. Showing the existence of an inverse, maybe we can keep aside for some time. Let's try to if there is a inverse, then it has to be unique. Okay. So question, uh, if A has an inverse mod M, then it must be unique. The downfall of the handwriting, but I think it's legible, so it's fine.
I think
So
inverses
any
are
idea as to how? Sorry.
multiplicative.
Yeah. Whenever I mention inverse, I will mean multiplicative today. It's
No,
just
no,
too
I
long to
mean,
write, and I have to think about the spelling.
no, I mean like
Okay. Yeah. What do you?
if I have A inverse and B inverse, then A inverse times B inverse will be AB.
You're stating another observation. Inverses are multiplicative. Oh, okay. I get that now. Okay. So what he's saying is that you have, if you want to find the inverse of AB, then that is just going to be A inverse times B inverse. The inverse of A is just going to be A inverse times B inverse. Interesting. So we will just quickly look at an example here to see what Riyans is saying. Riyans is saying, if I want to find the inverse of, let's say, 6, and 6 is 2 times 3. But so we can find the inverse of 6 by finding the inverse of 2, which is 4, finding the inverse of 3, which is 5, and then multiplying them together. So 4 times 5 is 20, which is 6 again. That seems to work like magic. I don't know. I feel like I feel like everything feels like magic when you first see it. I don't know. Yeah.
Because dealing with multiplicative inverses, I mean, here everything we do will be commutative, right? So that's a good property. In this particular case,
Right.
commutativity, it's pretty obvious.
Hmm.
And then that's why we
Hello?
have good things, right?
Yeah, exactly. So you're saying this just simply follows because of commutativity and associativity. So how do we show that AB inverse is just A inverse B inverse? Okay, now Okay, it's fine. So what we want to show is basically A inverse B inverse times AB must give us 1. That's what we want to show, right? And that would make this the inverse of AB. And this is just true because A inverse times A times this is equal to A inverse times A times B inverse times P. And this is 1 and this is 1. So this is just associativity and commutativity. So we're essentially using these core properties of how numbers are multiplied. This is just commutativity and associativity to conclude this. So the thing that I was talking about earlier, so this you can consider a very abstract form, something called a group. I won't go much into it. I'll just maybe talk like 1 or 2 sentences about it, where where the elements are not just like defined numbers. They're just like some elements that you know that you can apply some operation on. And they also follow some nice properties, like everything has an inverse and they're commutative and they're associative and stuff. Um, then in a group, this property always holds. Basically, the only you extract the properties that make this thing hold, and you call that, and you try to make it as abstract as possible and like detach it from the real world. Try to make it like an abstract quantity. Anyways, that was a divergent. That was an interesting observation and
Sorry.
nice proof as well. Yeah.
Vidya, I found one observation.
Yes, tell.
If any number m which is prime,
Hmm.
then whatever inverses we get, if uski power will always be 1 or -1 mod m.
Uski power, like power of
Like for
an
example, if
inverse. Huh?
power for example a raised to the power a inverse will be 1 mod that modulo m.
Oh, wow. Interesting. So you're saying 2 raised to 4 here is so you're saying 2 raised to 4 has to be 1 mod 7, is it? I don't think that's quite true because 2 raised to 4 is 16, it's just 2 mod 7, not 1.
Yeah, it is wrong. I tried another example, it worked in all cases. That's why I said.
Oh, I see, I see. Okay, interesting. It's all right though. It's all right. It would have been very cool if that worked. Okay, I think let's try to prove this. If there exists an inverse, then it has to be unique. I think this will open a lot of doors for us. Let's open some doors.
And prove by
Let's
contradiction.
prove by contradiction. Yes. So assume as- assume the contrary. Assume the contrary. So what do we assume? That we assume that A has 2 inverses, right?
But how can we show that it always exists?
That is something you will look at. Let's try to show that if it exists, then it's unique. So let's say A has 2 inverses. Let's call them like B and C. So let's say that AB is congruent to 1 mod M and AC is congruent to 1 mod M. So how do we show that they have to be equal? But there cannot be 2 inverses. How
AB
can we show that?
congruent to AC mod M.
Yes, exactly. And then,
Then A into B minus C congruent to 0 mod M.
yes,
GCD of A and M is 1.
yes, exactly. Those are very important things. You cannot just directly cancel A. The only reason you can cancel A here is because GCD of M and A is 1. I think this was one of the problems on your P set also. See, because GCD of M and A is 1, this tells us that M must divide B minus C, which means that B is congruent to C mod M. So B and C have to be one and the same. right? Does this make sense to everyone? Amazing. Okay. But this is actually even cooler because what is like stopping us from now saying okay, this is a very nice argument. What we are essentially saying, if you only focus on this argument, this part of the argument, is that if A times B and A times C are equal mod M, then B and C have to be the same, right? Do people see this? Like this is essentially what we're saying. And that actually tells us another very nice property. Does somebody want to say it out? So
Like basically, if I take the multiplication table of A mod M, then I'll basically
yes,
like AK is a permutation of K.
exactly. So this tells us that if we have any two multiples of A mod M, they have to be different. If you have two different if I'm multiplying A by two different numbers, the answer has to be two different numbers. Like AB and AC, if they are two different numbers, then B and C also have to be two different numbers. Or if let's actually go back to this and look at this multiplication table that we had. What this means is if you look at all of these numbers in this table, you're going to get all different numbers. No two of these can be the same. Do you see why no two of these can be the same? Simply because of this argument. If two of them were the same, if AB was the same as AC, then B and C would have to be the same. So everything has to be different. So if we list down all the multiples of A, like A, 2A, 3A, more, and so on and so forth, and uh, what is the last one? M minus 1 times A. These all must be different, right? Does this make sense?
Yes.
Okay. I like that people are speaking up more now. So, okay. That's quite neat. That's quite neat. And in fact, there's actually a very cool thing you can do from here, something that Rayans earlier mentioned, is that in the case of a prime number, in the case when m is prime, since all of these are going to be different, how many of these are there? There are m of these. No, m minus one of these. M minus one of these. They're all going to form, basically, we are going to get all the numbers from 1 to 1 to up till m
This is
minus
true
1.
because they all have GCD1 with the prime number.
Yes. Do people see this? Just these are just going to be permutations. It's basically just going to be, what that means is this is just going to be 1 to m minus 1 in some other order. Does that make sense to everyone?
Yes.
Okay. Now we do a very, very, very cool thing, which I like, but once you've seen enough things like that, it doesn't feel like magic. Um, what we do is multiply all these numbers. You multiply A times 2A times 3A, all the way up till m minus 1A. And we know that this has to be exactly equal to 1 times 2 times 3 times all the way up till m minus 1, right? So what do we conclude from here?
A to the power m minus 1 is congruent to 1 mod m.
Yes. A to the power. So the way we do that is we can rewrite the left hand side as a to the power m minus 1 times 1 times 2 times 3 all the way up till m minus 1. And we also have 1 times 2 times all the way up till m minus 1 to the right hand side. But then we can just cancel off this. Why can we cancel this off? Because this is the important part. We can cancel this off because m is a prime.
So all numbers smaller than m will have GCD 1.
Exactly. This is the main part where we use that m is a prime. Otherwise, till now we haven't really used anywhere that m. Have we used anywhere so far that m is a prime? I don't think so. Right? So since m is a prime, everything it's going to be co-prime with all the numbers smaller than it. That's why we can cancel off these things. And that tells us that a to the m minus 1 is congruent to 1 mod m. This is very cool. Right? What is this telling us? That for any prime p, if you take any number which is co-prime to it, which is basically any number that's not 0 mod p, and you raise it to that prime minus 1, you're always going to get 1. Okay? So maybe like does everybody, does this right? Does this make sense? Is this all good for people? So for example, over here, if we consider 7 as our prime, then we can look at 2 to the 6. What is 2 to the 6? It's 64, which is 1 mod 7. You can look at 3 to the 6. What is 3 to the 6? I don't know, something. It's just 27 squared, and 27 is
729.
1. So that's also 1. And 4 to the 6 is also going to be 1. I leave it as an exercise because I don't want to calculate. 5 to the 6, 6 to the 6, whatever. All of these are going to be 1. And 1 to the 6, I can calculate 1 to the 6 for you. You're welcome. It's also going to be 1. So that is very, very neat. I like this. Very neat. And in fact, we also proved it before we claimed it. We
You are
proved
giving the
it.
theorem without stating the theorem.
Yes, we should. Yeah, I stated it here though, right? That's
Right.
fine. Yeah. We already proved it, in fact. We proved the theorem before stating the theorem. So this is known as the Fermat's little theorem because it's so
And then we
little
can
and
prove,
tiny. Yes.
and then we can prove versions.
Sure. Hang on, but I just want to make sure everybody's on the same page. Fermat. Yes. I think the T is supposed to be silent. I don't know. I've always heard it. Anyways, my pronunciation, don't go on my pronunciation. It's like whatever. It's fine, it doesn't matter. Fermats. No, Fermats just feels very wrong. I've always heard it as Fermat. Anyways, is everybody on the same page? Any questions, doubts about anything we have been doing? Okay. Yes, I'm learning very new things. So Fermat was French, so the T is silent, at least in this case. Okay.
How to prove that inverses exist always?
Shivam won't leave me alone for this. He's like,
I am
how do
trying
you
that
know
from week 1
versus
I joined.
very, very interesting. I'm not sure if we'll have time to do that. Let me also mention this. So, another thing, another question I want to leave, I don't know if we'll discuss it, but is that okay, we got primes. Slightly edit this so that it works for
Multiply by a.
Sorry, I was just getting a call. Yeah. Um, yeah. So the question I was asking is, instead of, so another thing to think about is what could be something equivalent for non-primes. And keep in mind that the only place where we use that's a prime was this box where we cancel things off. So try to think about that. Maybe it's something for next class.
Can we
Okay?
multiply
Or
by
any other sorry?
can we multiply by a?
Can we multiply by?
Like in FLT, he's asking if we can multiply by. Basically, to
Multiply by
write,
a on both sides.
I think that's what he's.
Yeah. For this, also we were assuming GCD of a and m is 1. So instead, what we can also do is we can say also this is m prime, very important. So we can multiply both sides by a and get a to the m is congruent to a mod m. And this is in fact as it is like true for all a. A doesn't have to be co-prime to m. So for all a. So this is also like an alternate way to state the FLT. Okay. 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 Any other questions, observations, or any other like interesting things you want to explore, sort of, other than Shivam asking about why does universe exist in the first place? I'm also going to assume that one for why, and then we'll try to see another result. So 1 times 2 times dot 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 up until a minus 1. This is like a very interesting quantity. And earlier, as we saw, everything that has an inverse is going to be unique. And there was this other conjecture, right, somewhere about it being about inverses being paired up with each other neatly. So let's try to look at this interesting quantity. Let's try to look at what is m minus 1 factorial mod m. So what do I mean by this? If you don't know this notation, this just means 1 times 2 times 3 times all the way up till m minus 1. Okay. So let's try to look at this. Let's maybe look at some like small examples. Like m equal to 1, nobody cares. M equal to 2 also is like very easy because that is just m minus 1 factorial is 1. What happens when m is 3? Oh, somebody talk to me.
Hello, I said.
Hello. I didn't hear you. What did you say?
Yeah, it's 2.
2 and 4.
6.
2.
It's 6, which is 2 again. What about for 5?
It's 4.
4.
It's 4. Interesting. And what happens for 6?
0.
0.
Okay. 7.
6.
Okay, I'll tell you. I'll tell you. How are you calculating all of this so fast? So I'll say don't multiply all of this out. Be more clever about it. So how can you be more clever about calculating this fast?
Inverses.
Inverses.
6
Right.
into -1 mod 7.
6.
Yes. So 2 you can pair up with 4 that you know gives us 1. 3 you can pair up with 5 that you know gives us 1. So this is just going to give us 6. Okay, what happens for oops. What happens for 8?
0.
It gives us 0 again, right? Because you have 2 times 4 here. So it's just going to evaluate to 0. 9.
I think for any composite number greater than
0.
100.
Right. So now we can maybe conjecture from here that if we have a composite number greater than 4, then m minus 1 factorial has to be 0 mod m. It intuitively makes sense because if it's composite, then surely you will have two smaller factors that multiply to it, and it should work out. So maybe let's keep this aside and maybe we'll put this in the P set for you guys to prove later. But does this intuitively make sense at least? That if it's a big enough composite number, then surely m minus 1 factorial has to evaluate to 0.
And for
Right?
primes, it is getting -1 mod prime.
Yes. So for primes, if this conjecture of pairing up the inverses is right, then okay, even pairing up is like almost right, it seems, right? Because we're not exactly pairing things up because 1 is always with itself. 6 seems to be with itself. It seems to be that for primes, for 5 it was 4, for 7 it was 6. Maybe this much evidence is not enough, but I don't know. It's like calculating it for 11 and 13 maybe would be too much time and work. So the idea is that okay, so now the claim what we observe is that for prime, so I'll just since it's a prime, I'll just refer to it as P. P minus 1 factorial is always going to be P minus 1 or minus 1 mod P. And this is in fact Wilson's theorem.
It was conjecture and not proof.
Yeah, we have not proved it yet. So it's just the OMC conjecture for now. But unfortunately, like this guy called Wilson already conjectured and proved it
No,
back in the
Wilson did.
day. So Wilson didn't
Wilson did.
conjecture it.
Wilson conjectured it. He didn't prove it.
Wilson conjectured it but didn't prove it. Okay, my history is very kacha. Okay, so who proved it? Was it Fermat or somebody?
No,
Oops,
I think it was Euler only.
Euler only proved it.
But I
Okay,
think
fine.
Leibniz knew it before.
That is very confusing. It's fine. We don't. It's fine. What is in a name, anyways? But yeah, okay. So this is the idea, and okay, maybe I'll reveal some more things. So the idea is what we're going to try and show is that for a prime, except for 1 and p minus 1, everything else is is paired
I can
in an
show.
inverse. If you know it already from before, then I would prefer if you didn't talk about it. Okay, maybe somebody uh who has not seen it before can talk to me about it. Yeah. So everything is paired with an inverse. So if we can show this, then do you see why we'll be done? Because then we can just write this out. Then p minus 2, p minus 1. Everything other than p minus 1 and 1 is uniquely paired in something. So you have 2 with something, this is something, this is something. And this middle part will just evaluate to 1. And so you just have 1 times p minus 1, and then we'll be done. Right? Okay. Okay, so let's try to show that. But first of all, maybe something much more easier. Do you see why p minus 1 has to be paired with itself? Like why is p minus 1 always its own inverse? So what do you want to show? You want to show that p minus 1 is always the inverse of p minus 1 mod p.
P minus square is congruent to 1 mod P.
Yes, p minus 1 is in fact just essentially just minus 1. So minus 1 times minus 1 we know is 1 mod p. So p minus 1 is its own inverse. And 1 is its own inverse. In fact, this actually raises like very interesting questions also. Because now we know that 1 has two square roots mod p minus 1 and 1. So what about other numbers? Will everything have a square root mod p? How many numbers will be squares? And how many square roots will be there? These are like very interesting questions, and that also give rise to very interesting things in number theory. So maybe it's just like exploration mod. Yeah, now it should be better. Can you get it now? Oh, people went quiet again. It's only for today. Today I'm not at the usual place I'm at. So. But now it should be better. Can you hear me all right?
Yeah.
Yes.
We can also say that if P is a perfect square, then root P plus 1 square is also 1 mod P.
Okay, yeah. Okay, yeah. That's a discussion for another day though. I just left it as an open-ended question for you guys to try later. Anyways, yes, we have minus 1 times minus 1 is anyways, what are we doing? Yes. So now we will show that the only two numbers which have such that numbers x such that x square the only numbers x such that x square is 1 mod x is its own inverse such that x is its own inverse are 1 and p, sorry, p minus 1, and otherwise nothing can have like itself as an inverse, so it's going to be a part of some pair, and we know that assuming that there exists an inverse that we still haven't proved, but you guys believe me that it's true. Okay, so assuming we are anyways throughout the lecture today we have been assuming, maybe the next NT lecture can be about finding those inverses, but throughout today we have been assuming that there will always exist an inverse if the GCD condition is satisfied. Anyways, so this is what he will show, and do you see why this finishes? This finishes because
X square
um,
congruent to 1 mod.
yeah, this will finish because then since everything is a part of a pair and we have shown that everybody has a unique inverse, nobody has two inverses. So if everybody is part of one pair, all the pairs are going to be disjoint. And so they will all just multiply to 1 except for 1 and p minus 1. And then we'll be done. Okay? Okay, Gulshan said yes. And Ashutosh was also giving some good ideas. So Ashutosh, do you want to say it again? Okay, that's fine. So if x is its own inverse, that happens only if x times x is congruent to 1 mod p, right?
Yeah, so p divides x squared minus 1.
Yes, so p divides x squared minus 1 But we can factorize this and say, so P divides x plus 1 and x minus 1. But we know that P is a prime. What does that tell us?
Therefore, P divides either x plus 1 or x minus 1.
Yes, so P has to divide one of these, which implies that x is either minus 1 or 1 mod P. That's exactly what we wanted to show. Yes. Amazing. So now we're done. Right? That's exactly what we wanted to show. So done. Because then, as I said earlier, we can just multiply everything, pair up the inverses, and then the only remaining people will be 1 and p minus 1. So it evaluates to p minus 1. Okay. Okay. Now we still have some 10 more minutes. So there's been a lot of open-ended questions, but let me think which one of them we can possibly complete some sort of discussion about in 10 minutes. Okay, maybe we can. I think the best idea would be to have this a full circle moment, and also try to generalize Fermat's little theorem uh, to something for all numbers instead of just primes. Right? So what did we have earlier? So just to quickly recap, what we looked at was we looked at A, 2A, 3A, 4A up until P minus 1 times A. And we saw that this, oops, didn't mean to do that. This has to be a permutation of 1, 2, 3 up till P minus 1. And then just multiplied these. Multiplied to get FLT. To get A to the P minus 1 is congruent to 1 mod P. And the crucial step when we use that P is a prime was cancelling these 1 times 2 times 3 times P minus 1 from both the sides. Right? So now what is something that we can do here to... So now the only issue when we generalize this from a prime to n, any m, is going to be that you cannot cancel this. So what can we do to make sure that we can cancel both the sides?
You just multiply the numbers that are co-prime to.
Yes, exactly. So if we want to be able to cancel something from both the sides, the condition for cancelling, when can we cancel things? When it's co-prime to m. So what we do is we only look at instead of looking at all multiples of A, we look at only specific multiples of A. Only look at multiples of A, let's call them AK, such that K, GCD of K and M is 1, and K is coprime. Right? And then what happens? So then what do we get? So for example, let's restrict ourselves to, let's go back to the example of 8 that we had. It was somewhere here only. Yes. So let's say we want to look at multiples of 3. So we only look at multiples of 3 which give us numbers with the multiples of 3 which are co-prime to 8. So we look at 3 times 1 gives us 3. We look at 3 times 3, that gives us 1. We look at 3 times 5, that gives us 7. We look at 3 times 7, that gives us 4. And now, sorry, it does not give us 4. What does it give us? It gives us 5. Yes. So now this is nice again because this again gives us a permutation. Like if you look at 1, 3, 5, 7, it has come here as 1, 3, 5, 7 in some order. And now we can use the same trick again. We can multiply all of these and cancel these 1, 3, 5, 7s to get that 3 to the 4 is going to be 1 mod 8. Does this make sense? I remember the first time I saw this. I always talk about the first time I saw things. But anyways, I'll take a moment. The first time I saw this, my teacher was like, "Oh, give me any number." Then we were like, "Sure, you can take like something 15." They're like, "Tell me all the numbers co-prime to 15." You're like, "Okay, 1, 2, whatever, 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 whatever." And then he's like, "Okay, pick one of these and write down all the co-prime multiples." And no, he said, "Okay, no, that's not what he did." He said, "Okay, let's 1, 2, 4, not 6, 7, 8, 10, 11, 13, 14. He says, "Okay, how many numbers are these? 1, 2, 3, 4, 5, 6, 7, 8." He says, "There are 8 numbers. Now take any one of these numbers and raise it to the power of 8. You will always get 1." He said. And then I was just like, "Oh, how does that even work?" But then I thought about it for a while and then it made sense. But if you want to like again like if you have like some younger cousin you want to show them a magic trick, you can always just do this. uh, okay. Same reaction. Okay. Yeah. Um, right. Um, so basically that's the idea. And where is that? So how many numbers, what is the thing that we're going to get in the exponent? Basically, since we're only restricting ourselves to numbers that are co-prime to m, let's the how many ever numbers are there. So let's say there are 5 of m numbers co-prime to m. Then what happens is, okay, we have not proved this yet, but the first step to doing this is show that if we look at ak over all k such that ak such that uh, GCD of k and m is 1 if we look at this set, and also a is fixed, and co-prime to m. If we look at this set, then we claim that this is just going to be a permutation of the set of all numbers which are co-prime to m. This is like just written in some fancy way. All I mean to say is that if you take 3 and look at all multiples of 3 which are like co-prime to 8, then you'll just get back all numbers that are co-prime to 8 in some different order. Where did this? It went. Here. If you can do the same thing with 5 and look at all multiples of 5 which are co-prime to 8, you'll get 1, 3, 5, 7 in some order. If you look at all multiples of 7 which are co-prime to 8, you'll get 1, 3, 5, 7 in some order. And then you can multiply these out and then cancel out this product. Right? And then what you will end up with is basically that a to the phi of m, because you'll have phi of m numbers, right? In that set. So you'll have a, then you'll have uh, something, let's say it's an odd, let's say m is odd. So you'll have a, 2a, something times a, blah, 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 blah. You'll have phi of m such terms, which means that the exponent of a is going to be phi of m. And after cancellation, you're going to be left with 1. So you're going to get a to the phi of m is 1 mod m. And that's exactly like the sort of magic trick that I was trying to show here. It's like 4 to the 8, you get this one. And that simply follows from the fact that if you look at all the multiples of 4, which are co-prime to 15, you're going to get the same set in a different order. So you can cancel things because it's co-prime to 15. That's the entire idea. It's basically the same as the Fermat's little theorem, but just we are trying to extend it to any number. That's the idea. Does it make sense? Uh, yes, no, maybe, I don't know. Does it make sense? Gaurav, Arjun, Aishwarya,
Yes,
Shivam,
makes.
Ashutosh. Okay,
Yes, yes.
okay. Yeah. Okay, so this is called the Euler's extension of FLT. And this function is called the Euler's phi function. So now this gives rise to another interesting question to think about. Is there some way to calculate phi of m? Calculate phi of m. How do we find phi of m? If you're given m, how do we find phi of m? For example, we already know that phi of any prime has to be p minus 1. Right? Because the number of numbers co-prime to p is less than p is p minus 1. Everything is co-prime to p. But is there some way to generalize it to other numbers also? And yeah, I think there's like a lot of different questions that you can ask from here and solve.
Didi,
But this was, yeah.
are you from CMI?
I am not from CMI. But wait, so if you're done with the class, then I'll stop the recording and then we can chit chat say for some time. But let me make sure. Is there any doubt about anything that we have been doing? Then this is a very good time to ask. N. So I will take the N as a no.
Didi, can I show its proof?
The proof of what?
How to calculate phi of m?
That we can probably leave for another class in the future.
And my doubt?
And your doubt, I will just leave it to you to explore a little bit more. Try to find it, try to do it on your own. And if not, we'll obviously like have another class on it. So we'll discuss it then.
I
And
tried,
if
but
you,
no progress.
how long did you try?
Like whole lecture, I was doing that only.
Or try more. Try it for some a few more days.
Yes.
And yeah. Okay. All right. If there's no more questions, then I'll stop the recording. I'm
I have
around for another. Yeah.
I have one, but that is not related to number theory.
Sure. I will pause the recording.